Hello, good morning. Welcome to my workshop. I promised that I would do an update video on the changes that I've made to the Phoenix robot, and I'm going to do kind of a walkthrough here on the new audio system that I've designed and built for it. The idea behind this robot was to create what I would call a theater bot, an entertainment bot, a robot with the capability of saying scripted lines or actually interacting with people or other robots on the basis of a script. And the script is pre-recorded, and it is recorded onto a SD card. In this case, it's a 4 gigabyte SD card in the MP3 format, and the files are simply arranged by numerical order, starting with file number 1 and through the total number of files, which can be really any length at all. There's really no limitation on it. The board was built around the dimensions of the Lynx Motion controller boards. With the this is a bare board right here, and it has the hole spacing at the same 2.7 by 2 inch that the Lynx Motion boards have, so that it merely stacks on top of these other boards, which makes it really convenient to be able to use with one of these robots. The board itself is a 4-layer board. This one was made by Park, but nevertheless it was produced in KiCad, and it's a 4-layer board. I have found, working with audio especially, that 4-layer boards are more than worth their additional cost in their ability to mitigate problems caused by electrostatic discharge and EMI, RFI, and that kind of thing. So at this point, let me take you through the basic operation of the board. The board is powered by 9 volts. In my case, what I've done here is I've separated the power that powers the robot itself, the servos, from the audio, and I've done that intentionally based upon negative experience in doing it the other way. The voltage fluctuations that are present in the main power supply have a tendency to cause disruptions of the audio board, and they make its operation unreliable. So this board is powered by a 9-volt battery that simply sits here on the side of the robot. A 9-volt battery doesn't have an awful lot of energy in it, but it has plenty of energy to last a session of 20 or 30 minutes running the audio in this robot. The board and its associated amplifier, which is mounted underneath here, take about 80 milliamps. A 9-volt battery seems to be able to power the whole affair for 15 or 20 minutes with no difficulty. The 9 volts comes in here in this set of power pins, and runs through a 3-position switch into a 3.3 volt switching regulator, and then into the power plane. This board has a 3.3 volt power plane that goes throughout, and it also has a ground plane and 2 routing planes, one on the top and one on the bottom. Now, I'll just take you through the signal path here. The files are stored in MP3 format on this SD card, and the file playing is under the control of the main controller, which is an ATmega 1284P, which is a very capable 8-bit processor. The commands that cause the files to be played come in via this XB radio. It's a 900 megahertz XB Pro radio, in UART format, and they go to the processor, and the processor then commands the files to be downloaded from the SD card into a ring buffer within the processor, and then the audio is shifted over to the audio processor, which is a VLSI VS1063 audio processor. It's a very capable and easy to use processor that I highly recommend. I've used it in a number of projects. It works really well. The processor decodes the MP3 files and sends the audio out as two-channel audio, left and right, through this filter. It's a passive filter here that cleans up the audio signal. It goes through this device, which is a Digipot. It's a digital potentiometer, which is under the control of the main processor. It then goes into an amplifier, which is a preamplifier really. It's an OPA 2134 audio amp, and then appears on the left and right channels here. From that point on, the audio goes down to this amplifier board, which is an Adafruit 20 watt filterless digital class D audio amplifier. Very capable and cleanly running audio amp, which is powered by the same 9-volt battery that is running the rest of this operation. Now, I'm only using one channel of the audio at this time because I'm using the other channel to drive an LED, which I have placed upon the front of the robot inside this little speaker housing, which I'm using as a head for all practical purposes. It has a speaker in it. It consists of a cardboard tube which is acting as a speaker enclosure, which is really necessary for these small speakers in order to get any frequency response out of them. And the LED is right here, and the LED's purpose is to give a visual connection to the robot when you're looking at it, so that you can actually see that the audio is emanating from the robot rather than from someplace else in the room. I found that people can connect better with the robot if they can actually see the audio being made. It's a little bit like watching somebody's mouth move to prove that they're talking. And I'll demonstrate that in a moment. And I cut away for a few moments in order to hook up my lab power supply to the 9-volt DC power input. I'm using the lab power supply here rather than a 9-volt battery for this demonstration for a couple of reasons. Number one is I don't want to waste 9-volt batteries, and number two is it's easier for me to monitor the current consumption of the unit if I use my lab power supply. But the audio system is fairly simple. We just turn it on by flipping this switch. Hello, I am your friendly service robot. When you flip the switch, the audio system powers up and it just plays a little introductory message, which can be anything. It's just one of the files that are stored on the SD card here, so it can say anything. That's just what I have it saying. I also have put some demonstration files on the SD card, and I'll play those in order to demonstrate the operation of this little handheld controller, which is the mechanism that I developed to allow an operator to be able to play the audio that they want. Now, as I previously mentioned, the audio is stored on the SD card in numerical order, where each file has a file name that simply consists of a number. So it might be 1.mp3 or 91.mp3. The audio is controlled by simply turning on this little audio handheld controller and pressing the number of the file that you wish to play. Now, obviously you need to know what file is what number, and one presumes that you do because this is intended to be operated as though it's a script. The audio controller, I can simply press a number and then press the star key here, which is an enter key.
Hey Charlie, you got a quarter for a homeless man?
And the audio will play.
Come on, Charlie, lighten up.
And as you can see, there's relatively no latency to this. There is a little bit of latency, I suppose, but it's not really perceptible to humans. So it seems to respond pretty much instantaneously to the command. So I can press the command 3 and then enter.
Really, Charlie? Where's your sense of humor?
Or alternatively, I can simply step through the audio files by pressing the number key.
Come on, Charlie, give it up for a veteran. And I'm not going to hang around with you chumps.
And to turn it off, you just simply flip the switch. The software has an auto shutdown feature in it, which looks at the incoming signal here, and if it doesn't get any signal within a certain number of minutes, it will shut itself down in order to preserve battery power when no one is using it. To get it started again, you just simply recycle the power to the audio board and it'll start right back up again. The robot itself works exactly like the other Phoenix robots do, and it doesn't seem to mind carrying this at all. As I said, I did find that it was necessary to separate the power supplies, but other than that, it seems to work pretty well. I'm going to make the board available, the .pcb files, for anyone that's interested in. You can have the PCB files and you can build the system yourself, and I will also make the software open source so that you can copy it and use it as you see fit. I'll include a bill of materials list with the software and the PCB files. The build cost for the board is primarily in the cost of the audio processor. It's the expensive item out there. They cost about $10 in quantities of one. The other relatively expensive items are the XB radios, which cost $35 a piece, and of course there are two of them because there's another one inside this little receiver controller here. Well, I hope you've enjoyed the initial look through on this audio board, and as changes are made down the line, I will attempt to keep up with that and post that as well. Bye now.